Hello everyone, welcome back to the channel. My name is Dave, and in this video we're going to be taking a look at some golden trig identities. Namely, we're going to be calculating the exact values of the sine of 18 degrees and the cosine of 36 degrees. As the title of this video implies, both of these have something to do with the golden ratio. The idea for this video came from one of the comments. Hi Dave, sine of 18 degrees is equal to -1 plus root 5 over 4. Exactly why is sine of 18 related to the golden ratio? Well, in this video, we're going to find out and we're going to prove it. First of all, what is the golden ratio? Well, two numbers are said to be in the golden ratio if that ratio is equal to the sum of the two numbers over the larger of the two numbers. In algebra, we can write this as a over b is equal to a plus b over a is equal to phi. Now, if we rearrange this, we can get 1 plus b over a is equal to phi, or 1 plus 1 over phi is equal to phi. Now, phi plus 1 is equal to phi squared, and rearranging us gives us 0 equals phi squared minus phi minus 1. If we then apply the quadratic formula to this equation to find the solutions, we get phi is equal to 1 plus square root of 5 over 2, and we also get another solution, capital Phi, which is equal to 1 minus root 5 over 2. Moving on, let's first calculate the value of cosine of 36 degrees. To do this, we will draw a pentagon ABCDE. Then we will draw the diagonals EB, AC, and AD. We will label the intersection of EB and AC as point F. Since this is a regular pentagon, we can say that ABC is equal to 180 minus 360 over 5, or 108 degrees. Moreover, since ABC is isosceles, we can say that angle CAB is equal to 36. By symmetry, we can also say that angle DAE is equal to angle DAC, which is also equal to 36. This yields two similar triangles, ABC and ABF, which are similar by the angle-angle-angle theorem, so we can write them in the ratio AE over EB is equal to AF over AB. Cross-multiplying gives us AE times AB is equal to EB over AF. Since AE and AB are in fact the same quantity, we can write this as AB squared is equal to EB times AF. And since AF and FB are the same quantity, we can write this as AB squared is equal to EB times FB. Moving on, we can say that since EB is a diagonal of the pentagon, it's equal to EF plus FB. And since EF and AB are once again the same length, we can replace EF with AB to get the equation AB squared is equal to AB plus FB times FB. We can then distribute the FB and get AB squared is equal to AB times FB plus FB squared. If we divide through by FB squared, we get AB squared over FB squared is equal to AB over FB plus 1. Then we set AB over FB to equal x, and we can get the quadratic x squared equals x plus 1, for which the positive solution is phi. Now let's take a closer look at triangle AFB. We will drop a perpendicular from F down to AB and label that point of intersection as J. So as we said before, angle A is equal to 36 degrees and AB is equal to phi. This means that AJ is equal to phi over 2. Since AF is equal to 1, by the definition of the cosine, which is opposite over the hypotenuse, the cosine of 36 is 5/2. What about finding the sine of 18 degrees? It turns out that we can find this algebraically by solving the equation sine of the quantity 2 theta is equal to the cosine of the quantity 3 theta in two different ways. In the first way, we will simply determine the value of sine theta without finding theta. In the second way, we will find the value of theta itself. To find the value of sine of theta, we will use the double angle formula and the triple angle formula. Doing these substitutions, we get 2 sine theta cosine theta is equal to 4 times cosine cubed theta minus 3 cosine theta. If we divide through by cosine theta, we get 2 times sine theta is equal to 4 times the cosine squared of theta minus 3. Using the Pythagorean identity, we can get 2 times the sine of theta is equal to 4 times the quantity 1 minus sine squared theta minus 3. Substituting t equals sine theta, we will get 2t is equal to 1 minus 4t squared. And moving all the t's over to the left-hand side, we get 4 times t squared plus 2t minus 1 is equal to 0. We can apply the quadratic formula to this, and we would get t is equal to negative 2 plus or minus the square root of 20 over 8, which when simplified tells us that t, which is equal to sine of theta, is equal to negative 1 plus the square root of 5 over 4. But as we said before, we have to go back and we have to find what the value of theta is. In our original equation, we said that sine of 2 theta is equal to cosine of 3 theta. And knowing that the sine function and the cosine function are nothing but horizontal shifts of one another, we can write this substitution that cosine of pi over 2 minus 2 theta is equal to cosine of the quantity 3 theta. Since we have cosines on both sides, the arguments of the cosines must be equal. Therefore, we can say that pi over 2 minus 2 theta is equal to 3 theta. Moving the 2 theta over to the right-hand side, we get that theta is equal to pi over 10 or 18 degrees. Therefore, we can say that sine of 18 degrees or sine of pi over 10 is equal to 1 over 2 phi. With sine of theta, of course, being negative 1 plus the square root of 5 over 4, and phi being equal to 1 plus the square root of 5 over 2. So to conclude, our two golden trig identities are sine of 18 degrees or sine of pi over 10 is equal to 1 over 2 phi, and cosine of 36 or cosine of pi over 5 is equal to phi over 2, where phi is the golden ratio. If you enjoyed this video, please consider giving me a like and subscribing to the channel for future videos. Thank you for watching, and I hope to see you in the next video.